Hello, in this video we will go over eigenvalues and eigenvectors. So this is linear algebra and we're going to go over eigenvalues and eigenvectors. So we have gone over eigenvalues and eigenvectors in previous videos, so this one we're going to go a bit more in depth. So an eigenvector, whoops, so yes, so an eigenvector of a square n by n matrix is a non-zero vector x such that A times vector x is equal to lambda times vector x for some scalar lambda. So yeah, so let me just read this and then I'll do an example to explain. So A scalar, and then this is lambda is called an eigenvalue of A if there is a non-trivial solution such that vector x of A times vector x is equal to lambda times vector x, such that vector x is called an eigenvector corresponding to lambda. So what that really means is, in other words, a non-zero vector v is an eigenvector of matrix A if and only if the transform vector A times vector x points in the same or opposite direction of vector v. If lambda is an eigenvalue, If lambda is an eigenvalue for a matrix A, then the equation A minus lambda I times vector x is equal to 0 has a non-trivial solution. The set of all solution of this equation is a null space of matrix A minus lambda I. So this is a subspace of Rn and is called the eigenspace of A corresponding to lambda. Whoa. So what does that mean? So let me let me just go ahead and write that down. So what you need to know is note while an while an oops. So note while an eigenvalue lambda might be 0, an eigenvector is never going to be 0. So write that on your notes. And note an eigenvalue gives us a specific eigenvector. We are looking for the non-trivial solution. We don't want the unique solution. We want a free variable. So in this video, we are going to give you an eigenvalue and give us the eigenvector or the eigenvector giving us the eigenvalue. Okay, so let's do an example. So example one says let matrix A, this is a 2 by 2 matrix, of 0, -4, and -2, 2, and vector U is 1, 1. This is a 1 by it's a 2 by 1 matrix, and then this is a 2 by 2. And vector v is -1 to 1. Uh, are vector u and vector v eigenvectors of A? So what they're saying is, does this A times vector x equal to lambda times vector x? Is vector is vector u an eigenvector? Can we get lambda? Okay, so they're asking quite a few things. So okay, so let's do this part. What's A times lambda x? I think we have, oh, sorry, this is not x, this should be u because we don't have one. So this is A times u lambda equals to lambda times the vector x, right? So is matrix vector u an eigenvector? Can we get lambda? Let's see. let's see. So let's do the first, let's do this. So is A times vector U equal to lambda times vector U? We have everything we need. It was given that vector A, meaning matrix A is a 2 by 2, 0 times negative 2, negative 4, and 2. So this is a 2 by 2. This is ma this is matrix A times vector U. Vector U is given that is a 2 by 1, it's 1 and 1 equals does that equal to lambda times U? Let's do the so can we multiply these two matrix? This is a yes. This is a 2 by 2 and this is a 2 by 1. As long as these two numbers are the same, we're good. And it should be a 2 by 1. So go ahead and you should know how to multiply matrix. So I'm not going to review that. You should know. So this times this, that would be 0 times 1 plus negative 2 times 1. And then this times this is negative 4 times 1 plus 2 times 1. And that gives you negative 2, negative 2. If I factor out a negative 2, this is negative 2 times, and then this is 1 by 1, 1 and 1. So yeah, does this give you lambda times u, vector u? So what this means is this negative 2 is your lambda, and then this one and this 2 by 1 matrix is matrix or vector u. So what we did, we just proved A times vector u is equal to negative 2 times vector u. So negative 2 is your lambda, and then this 2 by 1, this vector is u. So we could say yes, vector u is an eigenvector, and lambda equals negative 2 is the corresponding eigenvalue. Okay, so let's do the next example. Oh, no, no. So there were, now remember they were asking two parts. The second part was asking, is vector u an eigenvector? So the second part of the question um, says, is vector u an eigenvector? Let's see. So is vector v an eigenvector? So what they're saying is, does a times lambda, a times vector x equals to lambda times vector v? Let's see. So we already know that vector matrix A is a 2 by 2. It is 0, negative 4, negative 2, positive 2, and vector x is negative 1, comma 1. And then lambda, we did this already. So when you multiply this out, This is a 2 by 2. This is a 2 by 1. So yes, you can multiply this out. It should give you a 2 by 1 matrix. And so when you multiply this by this, you get 0 times -1 plus -2 times 1. And then 4 times -1 times 2 times 1. So you should know how to multiply a matrix. If you could, or you could just put this in the calculator and you're going to get this 2 by 1, -2, comma, -2, 6. And then when you factor out a 2, it's going to be 2 and it's going to be -1 to 3. So it looks like this -1, this matrix, uh, it looks like this is not a vector, a V, a vector. So vector V is not an eigenvector. Vector V is not an eigenvector. Okay. Okay, let's move on to another example. Okay, so this one says, show that 4 is an eigenvector of matrix A of this 2 by 2, which is, uh, yeah, matrix A, and find the corresponding eigenvector. So what they're really saying is, we got to set it up like this. A times vector x is equal to lambda times vector x, right? And then what we got to do is get one side 0. So I'm going to have to subtract lambda vector x on both sides. Now you have a vector x minus lambda vector x is equal to 0. What could we do? Um, I think we could factor out an x. I mean, not x, vector x. So that would be, let's see, that will be, so if we factor out vector x, that's going to be a minus lambda times vector x to 0. And then that's going to be a minus lambda I times vector x. So what that means is it's going to be a vector x is equal to vector b. And then what we have to do is solve for vector x. It's going to be um, vector matrix A augmented with vector b. And that is approximately, so for this one, uh, so for this one right here, in order to get x vector x by itself, it's going to be A minus lambda identity matrix augmented with vector 0. And then make sure you row reduce. Okay, so that's what we're going to have to do. Um, so there's a lot of steps. So I'll go over step 1. So first step is let's do step 1. So step one, I'm going to set it up like this. I'm going to do A minus lambda times by identity matrix I is equal to A minus 4 times I. And that gives you, oops, this. So we know matrix A is 0, -4, -2, and 2. And it's going to be minus 4, and then 1, 0, 0, 1. So I think we're doing the right thing. Is that right? Don't check. Yes, I think we're doing the right side first. So matrix A minus 4 times the identity matrix of a 2 by 2. So this is I. This is -4, and then this is A. So let's kind of clean this up. So this is going to be 0, -4, -2, 2. And then when I distribute this 4, it's going to be minus 4, 0, 0, 4. And when you clean that up, you definitely can subtract these two matrices because it's 2 by 2. So you know how to subtract matrix. 0 minus 4 is -4. -2 minus 0 is -2. -4 minus 0 is -4. 2 minus 4 is -2. Okay, so that's step one. Now let's do step two. So step two, what we got to do is find vector x. So vector x is going to be equal to ma matrix A minus lambda divided by the identity matrix augmented with 0, or the 0 matrix. So that's going to be x equals. Oh yeah, so now what we're doing is the left side. Okay. So what is A minus lambda I? Um, it is going to be, it is going to be, so A minus lambda I is going to be -4, -4, -2, -2 augmented with, and we got a row reduce. So what we got to do is make this, what should I do first? Maybe make this -4 into a 0, and then maybe make this -2 to a 0. So how I would do that is I'm gonna do some row of operations. So row 2. So I'm messing with row 2. So this would be to make this -4 into a 0. All you got to do is do -1 row 1 plus row 2 gives us row 2. So when you do the work, you should get 0, 0, and then this is going to be 0, and then over here, this is going to be, row 1 hasn't changed, so this is going to be -4, -2, and then this is still going to be 0. And then what I got to do next is maybe make this -4 into a +1. So to do so, I'm going to do -1/4 times row 1, and that should give you row 1. So when I do that, I get 1, 1/2, 0, and then this is going to be 0, 0, 0, And then this column, 1/2 and 0 is what's called a free variable. Okay, so what that means is now we're going to have x1 plus 1/2 x subscript 2 equals 0. So x subscript 1 plus 1/2 times x subscript 2 equals 0. And when I solve for x1, uh, when I solve for x1, is going to equal to, so I would subtract this, so this would be negative 1/2 x subscript 2. And then when I solve for x2, x subscript 2 is equal to x subscript 2. So that gives me negative 1 and 2. That means is wait, so what that means is so we have wait, so this actually okay, so how did I get from here to here? All I did was multiply this by 2. So what it means is this is going to be, this was originally a vector negative 1/2, and then this is 1. I didn't like that fraction, so what I did was I multiplied both sides by 2, right? So I multiplied by 2, or scalar 2, by 2, and then that's how I got this vector. And that means lambda is equal to 4. Yeah, so that means lambda is equal to 4. And then our eigenvalue, vector x, is going to equal to negative 1 to 2, and then eigenvector or eigenspace. Okay, so I think that's yeah, that's it for him. So, okay, let's move on to the next example. Okay, so the next example says let S equal this S matrix, this is a 3 by 3, right? S equal this 3 by 3 matrix and lambda equals to 2 is an eigenvalue of S. Find a basis for the corresponding eigenspace, mean it just means find the eigenvectors. So what that means is, so yeah, you have this matrix 3 by 3, and we're given that lambda equals to 2, which is basically an eigenvalue of x. Find a basis for the corresponding eigenspace, meaning the eigenvectors. So how do we set that up? So what we're going to do is set it up like this. We're going to set it up like this. It's going to be a times vector x is equal to lambda times vector x is equal to a minus lambda times the identity matrix times it by vector x is equal to 0. So if you simplify that, that means when you solve for vector x, it's going to be equal to basically a minus lambda times by the identity matrix augmented with 0. Okay, so step one, what we got to do is first we got to find a equals lambda times identity matrix I. So what that means is, so we already know what matrix A is, so it's going to be matrix A is 2, -1, -1, and then 0, 3, and 1. And you have 0, 1, and 3 minus 2 times the identity matrix of a 3 by 3. So what is the identity matrix of a 3 by 3? It is this 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. So what we're trying to do is eventually what we're trying to do is do this. You want this to be like this. It's going to be 2 minus lambda, then a number like some kind of number. And then this would be 3, second row. This would be 3 minus lambda, and then over here would be a number, and then it's going to be 3 minus lambda. That's what we're trying to do. So when you simplify this part right here, or you can distribute that too. So yeah, that's our goal. So let's simplify this. So let's simplify this. So this goes right here. So this would be, so this stays the same. So this matrix is still going to be 2, -1, -1, and then 0, 3, 0, 1, 3, minus, and then this, when you FOIL this out, this is going to be 2, 0, 0, 0, 2, 0, 0, 0, 2. Okay. So when you just FOIL that 2, you get that. So when you subtract these two matrices, and you can subtract these two matrices because they're definitely 3 by 3, you get this. 2 minus 2 is 0. This is going to be 0. This is going to be 0. And this is going to be -1, 1, 1, and then -1, 1. And then we got to augment with 0. And then we got to row reduce. So basically what we did is we found this. So this right here, this whole step was basically a minus lambda times I augmented with vector 0. So now we got to do is so this is going to be, once we do that, that's going to be our vector x, and we gotta so we have this. So this, I'm going to put this down here. So this is going to be 0, -1, -1. This is going to be 0, 1, 1, 0, 1, 1, and then augmented with 0, 0. And then we got to row reduce. So what I have to do is I don't want the zeros. You see this row? I don't want that. I want a 1. So maybe I'm gonna have to switch rows. And I think I'll do is I'm gonna switch row 1 with row 3. So here's row 3, here's row 1, switch it. So I'm going to switch row 1 with row 3, and that gives me this negative 1, 1, 0, and this is going to be 0, 0, 0, and then this is 0. Oops. And then I gotta keep on row reducing. So now I want this negative 1 into a 0. So what I'm going to do is I'm going to mess with row 2. So it's going to be negative row 1 plus row 2. And that gives me my new row 2. And that gives me this. So row 1 stays the same. And then this is going to be 0, 0, 0, 0. And this is row 3 is still 0, 0, 0. Okay. Now what to do is now I gotta make this negative 1 to a positive 1, right? So what I'm going to do is I'm going to multiply the entire row 1 by the scalar negative 1. And that gives me this 1, negative 1, negative 0. And then this is going to be 0, 0, 0, 0. And then this is going to be 0, 0, 0. And this column right here, and then this column down here is a free variable. Okay, so now what we got to do is so now what we do is we're going to do, so this is a 3 by 3 matrix, so we're going to do x1 minus x subscript 2 minus x subscript 3, and that equals to 0. And then when you solve for x1, basically you have to add x subscript 2 and add x subscript 3. So this is going to equal to positive x subscript 2 plus positive x subscript 3. And then to solve for x2, so I'm kind of doing this in my head. So to solve for x2, we're going to have to subtract x1, so add x3, and then divide it by negative 1. So when you do that, you're just going to get x subscript 2. And then x subscript 3 is just x subscript 3. So, so if x1 equals to x subscript 2 plus x subscript 3, and then x2 is x subscript 2, and then x3 is x subscript 3, um, so our goal is to find the eigenvectors or the basis for the eigenspace. So we have that x equals x1, and then x script 2 is basically so yeah, x is equal to x subscript 1 times the vector. You get this would be 1, 1, 0 plus x script 3 times the vector 1, 0, 1. So if final answer is going to be, so my eigenvector is equal to the basis for eigenspace. And that's going to be equal to these numbers, I mean, these vectors. So it's going to be 1, 1, 0. And then this is, okay, so let's do another example. So on this example says let matrix A, just this 3 by 3, and eigenvalues of A are lambda equals to 0 plus or minus square root of 2. Find the basis for the corresponding eigenspace. Basically, find the eigenvectors. Then there's a keynote. It says whatever the size, whatever the size of your matrix, you need that amount of your eigenvalues. So that's a keynote. Whatever the size of your matrix, you're going to need that. You need that amount of eigenvalues. So what we're going to do is set it up like this. So you're going to say lambda equals to 0, which equals to basically, so it's going to be basically so the first number, A, matrix A was, I think, 3. So it's going to be 3 minus lambda, right? So it's 3 minus lambda, and then this is still 0, and this is -5. And we augment it 0, vector 0. And then this is number here. This was over matrix A had this number of 1/5. Let's say the same. And then it's going to be -1. Oh, so actually our lambda is 0, so that you could just replace this with 0. And then this is going to be -1 minus 0. And then this 0 stays the same. And then this was 1. This stays the same. This is 1. And the last term was -2. And then you have to minus that with lambda, which is basically 0, right? So what I'm doing is basically doing this. I'm doing 3 minus lambda, and then -1 minus lambda. This is -2. This lambda is 0. And then these are number, which is basically same numbers for matrix A. Okay. So then we got to do some augment. So let's clean this up. So yeah, this augment. 3 minus 0 is 3, 0, -5. Augment to 0, and then this is going to be 1/5. -1 minus 0 is -1, and then this is 0, and then this is going to be 1, 1. -2 minus 0 is -2, and then this is 0, 0, blah, blah, blah. And then you're going to augment it or row reduce, and what I'm going to, you could just put this in the calculator. I'm going to save you time. Yeah, you could just put this, so row reduce, put this in calculator, and you get this. 0, -5. And this is going to be element 0, this is 0, and then this is going to be, second row would be 0, 1, third, 0, and this is going to be 0, 0, 0, 0. So yeah, you could have just put this on calculator or just do the algebra. Okay, so what that means, this is my x1, x2, and my x3, right? So what that means is, yeah, so what that means is, x1 is equal to negative 5/3 x3, and then x2 is going to be, oops, this is positive because, yeah, and then x2 is positive 1/3 x3. So basically, so I'm kind of like doing this. This is gonna, so this right here is gonna be 1x1 plus 0x2 minus 5/3 x3 equals 0. So what I did was I kind of did in my head, this cancels, and then I just added 5/3 x3 sides. So that's how I got this. And then this one, this row is 0x1 plus 1x2 minus 1/3 x3 equals to 0. And then when you solve for x2, so this cancels, you're going to get x2 equals, so I have to add 1/3 x3. And over here it's 0, 0. So, oh, and then x3 is just x3 equals x3. Okay, so now we said that our lambda was square root of 2. Yeah, my lambda is equal to square root of 2, which equals to this matrix. 3 minus square root of 2, 0, negative 5, and then I'm going to use 0. And then this is going to be 1/5, negative 1 minus square root of 2, 0, 0. And then this is going to be 1, negative 2 minus square root of 2, 0. And then you're going to row reduce. So when you row reduce, you could just use a calculator. This is going to be 1, 0, negative 3.153. You could just put that in the calculator. Negative 0. And then this is going to be 0, 0.261, 0. And then the last row is 0, 0, 0, 0. So what that means is my x1 is 3.153 x3. Like I said, I'm doing this in my head. So remember, this is column one, x1, x2, x3. So this is like saying 1x1 plus 0x2 minus 3x3 minus 3.153 x3 equals to 0. And then I solve for x1 by adding positive 3.153 x3 to both sides. Okay, so my x2 is going to be 0.261 x3, and my x3 is okay. Okay, so remember it was plus 1 minus square root of 2, so now we have to do the same process when lambda is negative 2. So I'm gonna do that now. So when lambda is equal to negative square root of 2, I'm gonna get this 3 minus the lambda, which is negative square root of 2, 0, and minus 5, 0, and then this is gonna be 1/5. minus 1 minus my lambda, so that's minus square root of 2. And this is, and this is going to be 1, 1, and then negative 2 minus square root of minus square root of 2. This is still augmented with 0. And when you simplify this, this is going to give you 3 plus square root of 2, 0 minus 5. This is going to be 0, and then this is going to be 1/5. Negative 1 plus square root of 2, right? 2 negatives becomes a positive. This is going to be 1, 1, minus 2 plus square root of 2. 2 negatives positive. And this is going to be 0. And then when you finally row reduce, I'm definitely going to use a calculator because I don't have time. So when you row reduce, this is what you get. 1, 0, negative 1.133, 0. And then this is going to be 0, 1, 0.7, 0, and then this is going to be 0, 0, 0, 0. So what that means is, oops. So what that means is my x1 is equal to 1.33 x3, and my x2 is going to be negative 0.54 x3, and then my x3 is going to equal to x3. And it's going to give me, excuse me, can give me 1.30.547. This is going to be 1. So the after our answer, the last question says, so the question says find the basis for the corresponding eigenspace. So basically, we got to find an eigenvector. So our final answer or our final eigenvectors is going to be, so lambda is equal to 0, comma, plus square root of 2 minus square root of 2. So that means our eigenspace is going to be, our eigenvector is going to be, it's 5/3, 1/3, 1. This is vector 1. And then the next vector would be, so so when lambda was 0, this is what we got, this vector. When lambda was square root of 2 and we row reduced, we got 3.53, 0.261, and 1. And then when lambda was negative square root of 2 and we row reduced, we got this vector 1.133, negative 0.547, 1, right? Uh, if you don't want to deal with fractions, for example, here, 5/3, you can multiply it by 3, right? You can multiply this by 3 or multiply everything. So if you don't want to deal with fractions, you can leave it like this, or you can multiply everything by 3. That's fine. So I'm just gonna leave it like this. This is perfect. Okay, so that was the right thing. Let's move on. Let's move on to some theorems. So suppose lambda is an eigenvalue of A. Determine an eigenvalue for a square matrix and a general pattern for an. So yeah, so let me reread this problem. Suppose lambda is an eigenvalue of A. Determine an eigenvalue for the square matrix and a general pattern for an. So what we know is A times lambda vector x is equal to lambda times vector x. What I need is I need A squared. So what you're going to do is multiply both side by A. So when we do that, you're going to get A times A lambda x. I mean, A times vector x is equal to A times lambda vector x. And then this is going to be A times A is A squared. Matrix vector x is equal to A x. A vector x times it by lambda. And when you can simplify, this is going to be A squared vector x is equal to lambda. So when you do this, this is going to be basically, where is it? Okay, so it's A lambda x, and then this is A x lambda. So this becomes right here, this is going to be lambda vector x. And now you have lambda times vector x. So A squared times vector x is equal to lambda squared times x, or yeah, so this is your answer because it's in the form of an times vector x is equal to lambda raised to the n times vector x. Okay, so that's that simple, and then let's go over one last theorem, and then we'll end it here. So the theorems, so yeah, go over this theorem. So the eigenvalues of a triangular matrix are the entries of its main diagonal. So the eigenvalues of a triangular matrix are the entries of its main diagonal. So for example, this 3 by 3 is definitely a triangular matrix. How do I know? Because these numbers are all zeros, right? And then you look at the diagonals 10, negative 1, 2. So when you have that, the eigenvalue, these, I believe these are going to be your eigenvalues. So yeah, so my lambda or my eigenvalues are 10, negative 1, and 2. So if you can make this into a triangular matrix by making this 0, this 0, and this 0. And then over here, this is definitely a triangular matrix because it's 0, 0. So my eigenvalues or my lambda is the diagonals, just 3, negative 4, and 0. And then over here, yeah, so this is like triangle matrix, your lambda is 2, 2, and negative 3. Okay, so last theorem states, so this theorem states if vector v dot 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 vector subscript p are eigenvectors that correspond to the distinct eigenvalues lambda to lambda p of an n by n matrix A, then if v1 to vp is a linearly independent set. So what this means that if you have a unique eigenvalue, you are guaranteed to have unique eigenvectors. So unique slash distinct eigenvalues given distinct slash unique eigenvectors and the eigenspaces linearly independent. So this is going to help with the next lecture, which is on we're going to go over. So in the next video, we're going to talk about the linear algebra, the characteristic equation. So okay, so I'm going to stop here.